Hi guys, it's Mr. Y. Today we're going to be talking about half-life. So the learning objectives today are quite simple. Identifying what is half-life, how does half-life allow scientists to tell how old a fossil is, and to learn how to be able to solve basic half-life problems. So let's first start off by clearing up something. Half-life is a type of radiometric dating. It has to do with radioactivity. And radiometric dating itself is a type of dating system for fossils that gives an absolute time scale. Now, before the system was developed, people really couldn't tell how old fossils were. They could only say, oh, it's older than the layer above it, and it's younger than the layer below it. That's a relative dating system using the law of superposition. Whereas half-life systems actually give you a true number range to work with, like say 5,000 to 5,020 years old. Whereas relative dating, you kind of have to guess, well, it's older than this, and this is older than this, so everything's kind of a guess of this is between this, and that's not really giving you an absolute time scale if the layers of the sediments that you're looking at are kind of screwed up due to earthquakes or volcanoes or what have you. So half-life is a very, very useful feature for giving us an absolute time stamp on fossils and things of that nature. So let's go on to the definition of half-life. Now, half-life itself is a time. That's the first thing to figure out. It's always just a time. It may change, but it's just a time. And it's the time it takes radioactive elements to partially, 50% of the way, decay to a more stable form. So when you think half-life, think first off time. Think secondly, you're dealing with radioactivity, and it's the time it takes this radioactivity to get half the way gone, hence the name half-life. The first example I want to give you of a real-life half-life is with the isotope carbon-14, C14, right here. This decays, because it's radioactive, to a much stable form called nitrogen-14, and it has a half-life of 5,700 and about 30 years. It's actually 5,726 years, but we rounded 30. It's pretty accurate for what it is. Now, the symbol for half-life is always this little weird symbol here. This is called the lambda. Kind of looks like an upside-down Y. So the symbol for half-life is always this little lambda symbol. Another half-life that's important is potassium-40. K40, K of the periodic table of elements. This decays to a more stable form called argon-40. The half-life of this thing is about 1.3 billion years. That's a long time for half of the radioactivity to disappear. So it has a much longer half-life. And again, the symbol for half-life is this little lambda symbol. And again, that's 1.3 billion years. And another one to note that's important to biology, uranium-238, one of the largest natural elements we have. This decays to lead-206 over time. The half-life for this is 4.4 billion years. And you'll notice that, again, the half-life itself might change, but it's always a time. It's the time it takes for half of the radiation from either the carbon-14 or the potassium-40 or the uranium-238 to All right, now how this works out, this is a very simple methodology for thinking about it, and I do recommend you practice with this slide as you go. But how it works out is pretty simple when you get used to the idea. So suppose, for instance, you start with 32 grams of radioactive, let's say, element A. And I want to know how much is going to be left after 20 days if my half-life span is only 5 days. And there are things that have half-life in terms of days, not years. There are a few isotopes that have half-lives in terms of minutes or even seconds. But if my half-life in this case is 5 days, that's to say it takes 5 days for half of this radioactive element to decay to its more stable form, how much will I have after 20 days? So I'm going to do this first example visually. So suppose I have 32 grams of A and I have 0 grams of B, because that's the more stable form, and to start off with you have 0 grams, so just 32 grams of A. After one half-life, how much would I have? Well, I'd have half. I'd have 16 grams of A and 16 grams of B after 5 days, one half-life. But I want to know how much is left after 20 days, not 5, so I have to keep going. So what's going to happen after the next half-life? Again, I'm going to take half of the radioactive element. Now, this is where people screw up. They think, oh, you're going to have 0 grams of A and 32 grams of B. No, you're not. You're going to have half the remaining radioactive isotope. So instead of having 0, you're going to have half of 16, which is 8. And the other 8 went and turned into B. And because you already had 16 grams of B, 16 plus 8 gives us 32 grams. After another half-life, again, I'd have half of 8, which is 4. The other 4 turned into B, and now I have 24 plus 4, which gives us 28 grams. Thus, I have 28 grams over here. Now, how long have we been waiting so far? Well, so far we've gone through 3 half-lives. 1, 2, 3. So we've waited 15 days. I asked for 20 days, so we need to go for one more half-life. So what's the final answer going to be? Well, it's going to be half of what we currently have. Well, half of 4 is going to be 2, and the other 2 is going to go to B. That's going to leave us with 2 and 30. So after 20 days, or 4 half-lives, we're going to have 2 grams of A and 30 grams of B. And again, if we were to continue this process, you would take half. If you waited another 5 days, for instance, you would take half of 2, it would be 1, and then you'd have 31. Again, you're always taking half. And that's the key. Eventually, it gets down to the point where we can no longer detect the radioactive element A because you're down to the atomic scale, but it's always going to just take half of what's there. That's why it's called half-life. So, a full answer in 20 days or 4 half-lives. There's only 2 grams of radioactive element A left and 30 grams of B. To be truly complete, you'd have to answer how much of the stable form there is. But notice, nothing disappears. Nothing truly vanishes. You started with 32 grams. You still have 32 grams. You still have 32 grams. Every time, nothing is disappearing, nothing is vanishing, nothing is being created. You can't get something for nothing. Every time it has to add up to the same total. Nothing can just magically vanish. That doesn't happen in science. So if you're doing these types of problems and your totals are not the same consistently throughout, something is wrong. You've somehow broken a law of physics and you've done the problem wrong. All right, so the totals must always be the same. Okay, so we're going to try another one. This one I'm not going to do visually. I'm going to just do more mathematically. We have radioactive element C decaying to form element D in its more stable form with a half-life of 7 days. If you start with 80 grams down here, of C, how much is left after 35 days? Now, note there's no grams of D, and this is usually the situation. I'll explain why later, but sometimes it doesn't work as simple as this, sometimes it does. But our total here is 80, because 80 plus 0 down here is 80. So no matter what we do, it better always add up to 80. Now, if you're also paying attention to the half-life itself, you'll note for 7 days at a clip, we have to go for 35 days total. That means we have to go for 5 half-lives, 35 divided by 7. So we have to make sure we do this for 5 times. Now, if you go too far, if you go 6, you're not going to get the right answer. You go too short, you go for 4, you're still not going to get the right answer, even if you do everything right. All right, so let's get started. We start with 80 and 0. After 1 half-life, we are going to have 40 and 40. Half of C went to D. That's 1 half-life, 7 days. Now we need to continue. We go on for the next half-life. What are my numbers going to be? Well, they're going to be half of C, which is 20. The other 20 goes to D. Now it's going to be 20 and 60. Again, notice nothing has disappeared. Again, it always adds back up to 80, no matter what. It always adds back up to the total. Nothing magically just disappears. It just changes form. So really what we're looking at is the ratio between the radioactive C and the stable D. We're looking at the ratio between the two. After another half-life, Well, now we take half of 20, that's 10. The other 10 becomes D, so now we're at 10 and 70. So let's check. Where am I in terms of half-lives? How long have I waited? Well, 7 times 3, because there's 1, 2, 3 half-lives. So I've only waited 21 days. I have to continue. After the next half-life, I have 5 and 75. And again, that's not long enough. That's only going to be 28 days. I need to wait another half-life. So my final half-life after that, I have 2.5 grams and 77.5 grams. Now notice, again, everything adds back up to 80. Nothing has disappeared. So there's my final answer. I have 2.5 grams of C left, and I now have 77.5 grams of D. And if we were to continue, you'd have to take half of 2.5, which is 1.25, and add the other 1.25 to 77.5, etc. and continue. So let's try another example problem. In this case, I have radioactive element X decaying to form stable element Y with a half-life of 4 years. My question, if I start with 60 grams of radioactive element X, how much Y is created after 12 years? Now notice I changed the question to ask not how much of the radioactive element is there, how much of the stable element is there going to be after 12 years. So let's first figure out how many half-lives I'm going to have to use. Because I'm going for 12 years, that means I'm going to be doing this for 3 half-lives. So if you don't do it for 3 half-lives, you're going to get the wrong answer even if you know what you're doing. So once again, I set up my numbers. I have 60 grams of Y, 60 grams of X, 0 grams of Y. After 1 half-life, I'd have 30 and 30. After 2 half-lives, I've had 15 and 45. And after 3 half-lives, I'd have 7.5 half of 15 and 52.5 because I did 7.5 plus 45 grams to get 52.5. So the answer here is not 7.5 because remember the question is how much Y is created. So the answer is 52.5 grams of Y. And keep in mind, we use the word create loosely. Again, we're not creating it. It's just that's what's being transformed to by the radioactive element X. So again, when I say the word create, I'm using that in a very loose manner. I don't mean creating out of thin air. All right, now let's try this for a real-life fossil problem and see how this whole process works. Carbon-14, I mentioned this in the beginning, has a half-life of 5,700 and about 30 years. It decays to nitrogen-14. That's the more stable form. So carbon-14 is radioactive, nitrogen-14 is the more stable. And here's the problem. A bone of a fossil animal has 75 grams of nitrogen-14 and 25 grams of carbon-14. Assuming that there was 0 grams of nitrogen-14 when the animal initially died, estimate the age of the fossil. Now, a few quick things to note. One, because this half-life is so huge, this half-life from carbon-14 to nitrogen-14 is so huge, you can always assume that for animals, there's 0 grams to start because no animal lives for over 1,000 years. So no animal ever has anywhere near the total half-life span in its real life. So we always assume that it starts with 0. Now, carbon-14 is a naturally occurring isotope of carbon, and it exists in all animals, including plants. This is how we know the age of plants and dinosaur bones. So nitrogen-14 is a real isotope, a radioactive isotope, and it does really decay to nitrogen-14. So to estimate the age of the fossil, we have to take this problem and we have to work backwards. And here's what I mean. We know we found the fossil with 25 grams of carbon-14 and 75 grams of nitrogen-14. Well, if we're going to go backwards, we have to go backwards in time. So because half-life always goes forwards in time, now because we're going backwards, we have to reverse doing the whole half-life situation. When we reverse that, we double the amount of the radioactive isotope. So the half-life just before this started with 50 grams of carbon-14 and 50 grams of nitrogen-14. That's the only way it could have worked. Because if you had taken 50 and you did half of 50, it would have been 25. And the other 25 went to the nitrogen-14. That gave us 75 grams when we found the fossil. That was one half-life, 5,730 years. But notice we said, assume there was 0 grams of nitrogen-14 when the animal died. So this is not when the animal died. It's just when it's still dead and decaying. We have to go back further. Again, going back further, we double what we had for the radioactive isotope. So now we double the 50, we have 100 grams. And again, notice the totals haven't changed. We started with 100 here, and we still have 100 here total between the two, and now we still have 100. And now there's nothing of the nitrogen-14. This is when the animal died. And how long ago was this? Well, it was 2 half-lives, here and here. So this animal died about 11,460 years ago, give or take about 10 years. And this is how scientists are actually able to judge the age of fossils. They take what they know about half-life, they compare the radioactive element to the stable element, and they say, okay, if we assume this thing had 0 when it died and so much when it was, when it was alive, based upon what we see now, because the totals don't change, the totals are always the same, how long did it take to go from here all the way to here? And then they work the problem backwards. And this is how you get age estimates of fossils. Now, the reason we know half-life is consistent, and this is one of those interesting questions you should think about, is how, nobody lives for 5,730 years. How do we know the half-life of carbon-14 is always that? Is the way the atoms break down. And the way atoms break down, whether the half-life is 5,000 years, a billion years, or a few seconds, the curve of that breakdown is always the same. You start with 100%, you go for one half-life. After one half-life, you're at 50%. And again, that's one half-life. After the next half-life, you're at 25. This is percent, because half of 50% is 25%. That's your second half-life, and then you're at 12.5. And then you're at 6.25 for the fourth half-life. But the breakdown is always the same, meaning this curve, this line right here, always produces the same slope. Meaning we don't have to wait an entire half-life to know how long something takes to break down from one version to the next. We just have to know a little bit of this slope right here, and then we can tell, because this slope is different on every part, we can tell what the half-life is. Just by knowing a teeny tiny fragment of the slope, we know where we fall on the half-life curve. Again, this is the exact same thing, but this shows not only the breakdown of what we call the parent atoms, this shows the buildup of the daughter atoms. So this is the radioactive in the blue, like carbon-14, slowly decreasing over time. And again, that curve is exactly the same in every element. It's just the time that changes. Maybe it takes a few days for the half-life, maybe it takes a few billion years. But as long as we know a little bit about the slope, even for a tiny section, we can tell the entirety of the graph. And as the radioactive element breaks down, the number of daughter atoms starts to build up. So at the first half-life, you always get this 50-50%. So it's like if you had 100, you would be at 50 grams of the radioactive and 50 grams of the stable. And then after the next half-life, you're at 75% and 25%. And then you're at half of 75, so it'd be like 80 some odd. But again, the percentages are always the same, and the curves are always the same. So you just have to know a tiny bit of the curve here, and you can tell exactly how long the half-life will take based upon the slope of the curve. And again, the time itself really is kind of secondary. Once you know the slope, you can judge the time, and you don't have to be around to wait the entire half-life. So that's the idea with half-life. We can use this process to judge not only the age of fossils, but we use it to judge things as old as the Earth itself. Because remember, certain half-lives go for 1 billion years, like uranium. That's how we can actually judge the age of partially judge the age of the universe and the age of the Earth and the age of the moon. Because they have such long half-lives, we know they've barely gotten through their first half-life in some cases, or they're only on their second half-life in some cases. So using half-lives of longer span lets you look further back in time. Using half-lives of shorter span lets you get more accuracy, but you can't look further back because after a while you lose the ability to measure the radioactivity after this point because it gets to a such small degree of radioactivity. So that's half-life, guys. Make sure you're at least good on the practice problems and ask questions if you have any in class.